Hello and welcome to another walkthrough. Now this time it will be Edexcel AS Further Maths Core Pure Paper 1, May 2025, which I have never seen before. So this is going to be a blind solve for the entire paper under the real exam conditions. So along the walkthrough, I might be making mistakes, which I'll correct if I realize in the walkthrough. But if I don't, I'll annotate the video and I'll try to explain the worked solution and the thought process as simply as possible. At the end of the walkthrough, I'll mark the paper anyway. For those of you who make mistakes a lot of times, you might benefit from seeing me making a mistake and correct it later. So this walkthrough is not meant to just show you the destination of the solutions, but also show you the journey to the destination. If you feel like jumping to a particular question, you can use chapters in the description. Otherwise, stick around. You might be getting some tips along the way. If you are ready, I'll see you in there. Hi guys, just a quick one here. This statistics always blows my mind. So as you can see, for the past 28 days as of today, more than 90% of those watch hours come from those of you who aren't subscribed to my channel. And that gives me an urge to beg you, please help support me by subscribing the channel. I will return this huge favor by creating more and more videos. I'm going to utilize my teaching experience for 10 plus years to create the videos covering tips and tricks and the hard bits in the topics that most students struggle to understand. It can either be a short video, a long video, but they will sure come up. So that is why you need to subscribe to stay tuned. I hope we have a deal. Let's get back to the walkthrough. Okay, here's the paper and I'm going to start the timer now. Okay, let's get going. I'm gonna write in on the right side here, and this is the paper I'll be looking at so you guys can see too. Number one, write z in the form of r cos theta, I sin theta. So that's called a polar form. So part A here. Well, we can find r by just finding the modulus, or a Pythagoras, should I say, of that and that. Basically just the x, the y components there. So this is the square root of 3 plus 9, which is the square root of 12. Okay, and that would be 2 root 3, so that's r. And theta is basically the argument of the z. Now we gotta be careful here. We can't just do arctan always, because there is like an angle we need to consider here, like the coordinates. So this is root 3 for the x, root 3 for the x, and minus 3 for the y, maybe around here. So it's this angle here, but the argument is in the domain of minus pi to pi. So we need to choose the angle that is smallest to the x-axis, which is this angle. But then we make it negative, because if you want to make it positive, then it would have been this, which is over the pi. So we need to make this a negative of that physical size of the angle. Now, how do we find that angle? Well, basically, this is just this physical size here. Yeah, this little angle is basically just arctan of 3 over root 3, right? Because the y is 3, the x is root 3. I just take the positive value there. And 3 over root 3 is just root 3. So arctan of root 3, I happen to know, that is, which is 60 degrees, or pi over 6. Sorry, pi over 3, yeah? So, yeah, arctan root 3 is pi over 3, so that will be minus pi over 3 instead for the argument there. Okay, so we write the form now because we got it now. So I is 2 root 3, and that would be cos minus pi over 3 plus I sine minus pi over 3. So that would be the answer there. Yeah, we already satisfied the range of the theta there, which is in minus pi to pi range. Okay, part B, show and label on a single Argand diagram I, the point P representing Z. Okay, so an Argand diagram. Okay, so this is real of Z. This is the imaginary part of Z. Okay, we have a point Z here. Well, I actually did that in part A. So it's just root 3. I'm going to make this root 3 then. And this is minus 3. So that's the point P. Okay, that's point P representing Z. And point Q representing IZ. Well, IZ, right? We need to do some math here first. So I times root 3 minus 3i. That's I times Z, basically. So it is actually, if you multiply this I times I is minus 1, so minus 1 times minus 3 is 3, so the real part becomes 3 instead here, and the imaginary part become root 3i. So that would basically be 3 around here maybe, yeah, and root 3 would be maybe around here, so that's the q instead. Okay, so that's the point q there. Let me just check my math there. Yeah, I think I'm happy with that. It's just, yeah, kind of like swapping the coordinates there. Okay, so this is iz. Okay, so I'm done with part B here, both of the subparts. Part C. Describe the geometrical transformation that maps P onto Q. All right, so P onto Q, right? Well, how about we're gonna consider each one of them P onto Q. Okay, we can try get the matrix here first. So this is matrix A, which is the transformation matrix. I'm gonna make it T times so the original point P is 3 root 3, right? And after multiplying that transformation matrix, we get, wait, it's not that, sorry. This is the original, so it is root 3 minus 3, and the final one we got 3 root 3, right? Okay, right. Well, I mean, one way to go is to think about like A, B, C, D here. I mean, that could be one way, and then once we got all the coordinates or the variables A, B, C, D there, we should be able to think about the geometrical transformation from P to Q. But I would say it's basically a rotation, because it feels like a rotation here. It shouldn't be a reflection. I don't think so. Or it is a reflection. Is it a reflection? I think it should be a rotation, like a rotation, you know, anti-clockwise 90 degrees. Well, actually, let's assume that it is the case, yeah? So if that's the case, then I have this line and this line. I mean, to make this make sense, these two distances have to be equal if it's a rotation, right? So this is 3 by root 3, yeah? This is also 3 by root 3. So I think definitely if you do the Pythagoras for those two, you get the same distance. All right, check. Now what about the angle? Well, do these add up to 90 degrees, right? I mean, look, if we find, you know, you can try find the tan theta for this. So this is, okay, let's do that. So this angle here would be arctan, yeah, root 3 over 3. And that is basically 30 degrees, isn't it? Yeah, arctan of 1 over root 3. And this, we already got it to be 60, right? In part A. We did the arctan for that to find the argument. And they add up to 90 degrees. So, yeah, this is a rotation. Anti-clockwise by 90 degrees. That's it. So, I didn't need to do this. I mean, that would be the last resort. Yeah? So, you equate, like, you multiply all out here, and then you think about what should be A, B, and C, and D. But that's still tricky, actually. That might not be a viable method there. So I would say just try assume first and inspect backwards if it works. So I'm just going to say here rotation. And of course, I didn't mention that it is rotation about the origin. Yeah, rotation anti-clockwise by 90 degrees about origin. That would be enough to explain everything. Yeah. P onto Q. Yeah, I think I'm happy with that. So let's go to the question 2. Yes, question 2. Given that f minus 5 is equal to 0, so that is saying that z plus 5 is a factor of that. Okay. Part A, determine if z in the form of that. So we have a linear factor z plus a and a quadratic factor. Okay. So you can do a long division here. Yeah, let's do a long division. So z plus 5, because the critical value was minus 5 there, and we're going to do long division. Okay. So let's put 4z cubed minus 12z squared minus 95z plus 325. Okay, let me move that down a little bit. Okay, yeah. So the first divided into the first, we get 4z squared, and then multiply all out back to the divider, we get 4z cubed. That's the point because they cancel now. Plus 20z squared. Subtract both of them, we get minus 32z squared here. Pull the next one down, 95z, and divide the first into the first again. We get minus 32z squared here. And then multiply that back to 5 there. So it would be minus 160, right? 32 times 5, yeah. Z, and subtract this again, we get 160 minus 95, so that would be 65, right? Yep. 65 Z plus 325. Yeah, and then the first, divide into the first again, this is 65. That should work, so we get 65z plus 325. Yeah, and that will subtract to 0. Okay, so that means if z would be z plus 5 times, this is 4z squared minus 32z plus 65. Okay, so that's it for me. Part B. Hence show that the complex roots of fz equals 0 are that. Well, basically we just solve the quadratic there. Okay, so solving the quadratics, just use z equals plus or minus, wait, hang on, minus b first, minus b, minus 32, I mean because minus b there, plus or minus square root b squared minus 4ac, yeah, just focus on the quadratic, divided by 2 times a, yeah. And then we should expect to get 8 plus or minus I divided by 2. It's a complex root there. So in the square root, what do we get? 32 squared. I need a calculator there maybe. Where's my calculator? Okay, let me pull out my calculator here. Okay, just wait a bit. So square root 32 squared minus 4 times 65. Okay, so that would be 4i, so this is 4i and 32 here and divided by 8 here. Yeah, and if you cancel that by 4 in every term, you get 8 here plus or minus I here, divide by 2 here. Okay, yeah. That's the complex roots there. Determine the values of z such that f 2z minus 1 is equal to 0. Well, basically, okay, you got to imagine first that the values of z such that this, okay, it's a transformation. But basically, because, okay, hang on. I mean, basically you just plug this into this, right? But you already got all the roots. Yeah? So this is basically, what does it do here? It basically shrink the x-axis by half and shift to the right by 1. Okay? So the x-coordinate on the real part, like the Argand diagram, it will be shifted to the right by, it will be divide by 2. Yeah, the x-coordinate here, I'm just going to put like that, x-coordinate, divide by 2 because that multiplies z there, and shift to the right by 1. Okay, and that's going to happen to all the roots, basically. Okay, so from minus 5, then it would become minus 5 over 2 plus 1, and that would be minus 3 over 2. And for the 8, so we have 8 plus minus I divided by 2. It would be, so we divide the whole thing by 2 first and shift it by 1. It's only going to affect the real part, basically. All right. So that's going to be 8 plus or minus I over 2 divided by 2, right? And plus 1. What's that going to be? So that's going to be 8 plus or minus I divided by 4 plus 1. What's that going to be? So 1 is basically 4 over 4. So that's going to be 12, right? Yeah, because you add 4 to 8, you get 12. And plus minus I is still the same and divide by 4 here. So those would be the two complex roots after the transformation. All right, and that's it. Okay, that would be my answer there. I think everything is okay here. Let me just double check. Yep, I think I'm happy with that. All right, so number 3. Where a and b are real constants and a not equal to b, determine inverse m in terms of a and b. Okay, right. So inverse m in terms of a and b, well, for 2 by 2 matrix is easy. So we find the determinant of m first. The determinant of m would just be a times minus 1 minus b times minus 1. All right, just cross down minus cross up, right? Yeah, that's normally the way to go. So this is minus a plus b or b minus a. Yeah. Okay, and then the adjoint of 2 by 2 matrix would be, yeah, just swapping the a and the d. So I get minus 1 and a here, swapping these two, and put a minus sign into the other two, like that. That's the adjoint of 2 by 2 matrix. And because any inverse matrix would be 1 over determinant times the adjoint, yeah. So that's m inverse. So that's going to be 1 over b minus a, and the matrix of the adjoint would be minus 1 minus b, 1a, like that. Yeah, okay. In terms of a and b, yeah, that's done. Now part b. Given that m plus m inverse equals I, where I is 2 by 2 identity matrix, determine the value of m, a, and b. So yeah, we're just going to sub everything into that equation because we're given that. This is m plus the inverse of m, so 1 over b minus a, minus 1, 1, minus ba here. And they add up to the identity, which is 1, 0, 0, 1. Okay? So that's it. Well, we're just going to look at, let's see, which one is easy here? Okay, so how about I look at this component, right? So I'm going to have minus 1 plus those equals 0. Yeah, I mean, like it or not, we're going to have this in every component we do. So I'm just going to pick the 0 here first, like the top left, bottom left, yeah, component, 0. And then I have minus 1 here from that, plus 1 over b minus a from the other one. Okay? If you multiply by b minus a, or to all the terms in the equation, you get a minus b here for multiplying with 1, minus 1. And this will be plus 1, this will be 0. So that is saying that b equals a plus 1, right? That's equation 1 maybe. And then if I pick similarly, how about I pick this one, yeah? Or should I do, yeah, I mean, that's probably not much of a choice there. So I'm just going to do this one right here, yeah? Bottom right, so equal 1 on the right. And then I have minus 1 here for the first one, plus, that's a over b minus a equal 1. I move minus 1 to the other side, I have a over b minus a equals 2, right? Just plus 1 on both sides. And then I multiply out, I get a equals 2b minus 2a. So that is saying 3a equals 2b. Yeah? Well, we want to find both of them anyway, so I'm just going to do b equals 3 over 2a, and that I'm going to sub that back to this. Back to this, yeah, to solve for a first maybe. So that means 3 over 2a equals a plus 1. Okay. Subtract a both sides, I have 1 over 2a equals 1. That means a equals 2. Sub that back into this definition here of b, so I get 3 over 2 times a, which is then 3. So a equals 2, b equals 3, yeah? That makes sense, at least to the set of equations I have here. Let me double check that. 3, yep. So a is 2 over 1, yeah, everything works. Okay, that's it for number 3. Number 4. Okay, part I. Given the matrix P here, describe fully the single geometrical transformation P represented by matrix P. Okay, so I think the easiest way to describe the transformation by a single 2 by 2 matrix like this is to think about the original matrix 1 0 0 1. This is basically the identity matrix, but you look at this in a column-wise way like that. So you look at that, the first one represents the unit vector along the x-axis. Let's name that vector I. Yeah, along the x-axis, a unit vector along the x-axis, and let's name this vector j, 0 1 and 1 0. So this is the original. Now if we have a transformation matrix that has 2 0 and 0 1 here, and this will be the new I, let's call that I prime, and this is the new j, let's call that j prime. You see, the vector I is kind of like from 1 0 becomes 2 0. Isn't that like a stretch by 2 times? While the vector j doesn't change a bit, right? So this is only stretching along the x-axis by a factor of 2. So that would be the description. Easy, yeah? This is part I. So yeah, stretching along the x-axis by a factor of 2, or some people might prefer saying dilate along the x-axis, like just one direction. Yeah. Okay, so that should be it for part A. State the equation of one invariant line under the transformation P. One invariant line. So the line that doesn't change under this transformation. Well, let's get some drawing here first. Okay, so that's the x, that's the y. We have an I here and a j here. But after the transformation, it becomes like that. I prime and j remains the same. Well, okay. So we are basically putting a line, an equation of a line that wouldn't be affected at all by this transformation. Let's think about a normal linear equation, right? Let's say y equals x. You know, honestly, I forgot about this. It's been a while. So this is how I would go about it. If you have y equals x, or even just a normal linear equation mx plus c, and if you put it to that transformation, look, all the x coordinates of the line, on the line, will be sort of like stretched, right? Because it's going to be stretched by 2 times. So in this case, this line would look like that, because this point will be stretched by 2, this point will be stretched by 2, either way. Yeah? Now, what kind of line will not get changed? Well, is it the horizontal line then? Because if we have a gradient, it's going to change. So you don't have many ways of having a straight line. You can have a normal straight line with a gradient of non-zero or non-infinity, but it would change here. How about this kind of line? So this kind of line is y equals some value 2. Well, all the x coordinates here will be shifted, right? Wait, hang on. That's not y equals 2. This is x equals some value, k. All right. Well, yeah, it's going to be shifted to 2k instead, isn't it? That means the horizontal line will not change, y equals k. Because, you know, whatever points you consider here is going to be shifted, but still along the same line. Right? And that doesn't matter to the looks of the line. We still have the same line. You can try think about that. Because the y coordinate here isn't affected by the transformation. So we're going to go with that. The equation of one variant line under transformation. Okay. One invariant line. So I'm going to go with y equals 2. All right. Yeah. Oh, let me put y equals k as well here, just in case. Yeah. All right. yeah, part II, we have that matrix Q. Matrix Q represents the transformation Q. Triangle T is transformed to triangle T by the transformation Q. Okay, so all right, so triangle T is transformed by transformation Q to triangle T prime, like that. Given that the coordinates of vertices of T are that, and that, well, okay, the area of T is that. Okay, determine the possible values of theta here. All right. Okay. So, well, let me write down everything here. Yeah, like that. Yeah, just put the elements of all the matrices in, and well, you have 3 coordinates here of a triangle, so you need to put in columns like this: 2, 3, 3, 6, and 8, 3 for the T. Yeah, for the triangle T, and that's going to be transformed to something here. Okay, now because we know the area of T prime, so I think the way to go with this is to use determinant. Yeah, now let's use the kind of like the determinant is not exactly determinant because you can't find determinant of a non-square matrix here, but let's find the area of T. So that is by doing 1/2 and kind of like the determinant way, but this is the way we do it. So you put all the coordinates in this way: 2, 3, that's the first point, 3, 6, 8, 3, and then side click to the first point, back to the first point. Okay, so I have 2, 3, 2 of them here. And then you do multiply down minus multiply up. So multiply it down, I have 12, 9, and 24 here. Multiply up, I have 9, 14, and 6, right? So we're going to do 1/2, 12 plus 9 plus 24, and then minus all the multiply up. So 9, 14, and 6. Like that, yeah? If in the brackets it happens to be a negative number, we change it to a positive. No big deal. So I'm going to do modulus here, yeah? So that's the area of the triangle T. So it's 1/2. What is this? 21, 45 there, minus 29, right? So 45 minus 29 times 1/2, I get 16 in the brackets, right, in the modulus. And then 16 over 2, I get 8. Okay, so 8 is the original area. Let me double check the math there, just in case, yeah? Checking everything I did with the determinant method there. Wait, hang on. Uh-oh. This is 9. What is this? Why is this 14? Oh no. Good that I double checked. This is 4 times 8. It's 48. Oh man. Okay. That should be 48. Yep. 3, 6, 8, 3. Yeah. Should be 48. Okay. So 48 instead here. Right. Okay. Hang on. Right. Okay. So it's not that now. It's 45 minus. So 9 plus 6, I get 15. 15 plus 48, I have 63, right? Yep. And what is that then? So that is 15 to 60. Wait, hang on. 15 to 60, and then 18. Yeah, so that's negative 18, so that's going to be 9. Aha! Makes more sense because 9 is like twice 2 times 4.5, right? Yeah, let me double check that again. All right, yeah. Could have just used a calculator, guys, but that's just my habit of not using it. I don't know why. Area of T prime. Okay, now we know that when we talk about area, right? So when you have transformation Q, the determinant of the transformation matrix, which is Q in this case, will be the area factor. Yeah, so it will be the area factor. that you go from t to t prime. Okay, so that means t area of t prime here will be determinant q times, well, determinant might be minus, so this should be a modulus, times the area of the original t. And now we get the area of t to be 9, right? And this to be 4.5. And this is determinant q. That means the determinant q should be 1 over 2. 4.5 divided by 9 there. Okay? And because we know also that the determinant of q is just cross down minus cross up, right? So cos 2 theta times tan 2 theta minus 0. Okay? Because 1 times 0 is 0 there. So what is this then? This is basically cos 2 theta times sine 2 theta divided by cos 2 theta, right? Well, okay, we got to be careful here, because if we want to cancel cos theta out, I mean, we could do that, but will that omit some value there? I think it won't, because we didn't cancel either side. I think we're good. Yeah, we can cancel that out. And that will be sine 2 theta equals 1/2. Now, theta is in the range of 360 to 0. So that means 2 theta is in this range. I mean, this is pure math now. You should be familiar with this, because you got to be careful. You might get a lot of theta answers, theta values here. Well, but sine of what angle gives me 1/2? Well, using a cast diagram, right? We can do 1/2 is a positive, so we get these two lines. So that means 2 theta might be 1/2. The first 1/2 is pi over 6, right? Because sine of pi over 6 is 1 over 2. Or you can get the other quadrant on the second quadrant there to be 5 pi over 6, right? Just pi minus pi over 6 there. And then you can go another round, because this is not the end yet. Well, actually, I should have done the degrees. So this is 30 and 150. So what we're going to do here is just keep adding both of the answers by 360. So the other two would be 390 and 410. No, that's 510 actually. 360, yeah, should be 510. Okay, like that. Adding 360 to either one. And that's it. Because if you add either one of these by 360, you're going to go over the domain now, more than 720. And then that means theta would become, just divide everything by 2 here, right? So you get 1575, what's that, 190, hang on, no, is it? Yeah, 195, right? 195, yeah, and 255, right? Yeah, so that would be all possible values of theta. Okay, so that would be it. Yeah, and this is a cast diagram, so that's 30, and this is 150 there. Okay, so that's it for this part here. I'm gonna go to the next one. Next, number 5. A complex number z is represented by point P in the complex plane, given that z satisfies that. That looks like a circle, loci. Okay? A sketch on an Argand diagram, the locus of P as z varies. Okay, so, I mean, if you have this form here, you should all know how to shade all the types of region from this kind of equation, right? When you have z minus z1 in modulus equals 1 here, this will be the radius. Okay, basically the radius there. It's basically saying from point z1, whatever that is, and you have all other point z here where the distance, so z minus z1 there is telling you about the distance between the point z and point z1. So point z1 is a fixed point, but point z is any point. But it has to be the distance 1 unit away from z1. So that is indicating a circle, because, you know, if you go around in 360 degrees, you will have a fixed distance of 1, right? About a fixed point. Yeah. So that's the locus of P. Now, but we need to put z1 exactly where it is. And because we have minus 1 here, this Z1 will translate to a point 1, 0, right? Because we don't have any complex part there. Sorry, the imaginary part. So that means this is 1, 0 here. And then we have a circle of unit 1, so that should look something like this, because the radius is just 1, so that should hit the y-axis like that, yeah. That's it. So this is 0 here, this is 2, okay? Just like that. And this is 1, this is -1, this is real part, this is imaginary part, like that. Okay, so that's the locus of P. Part B. Given that Z also satisfy argument of Z plus 1 equals theta. Well, this will be a half line, yeah? So what do we do? Hang on. Determine the possible values of theta such that the locus argument Z plus 1 equals theta is a tangent to the locus of that. All right. Okay, so we're gonna copy this thing and then consider the second part now. The circle is fixed here because it's from part A, but we want such that the half line is a tangent to this. So how can we make that half line a tangent to this? Well, we can have this, right? Okay, let's talk about the half line first. Theta. Okay. Yeah. So it might look like this. Yeah. Oh no, it's also Z plus 1. So this is from the point -1, 0, right? Just the same concept there when you have a Z minus something or Z plus something in the argument. So this is reference to the point -1, 0, which is here. Yeah. And we have a half line from that point. So, okay, like that. Yeah. Determine the possible values of theta. So that's one way. That's theta. That's one of them. And we could also have a negative value, right? A half line of a negative value. If the theta is negative, then it's just the other way. If theta is positive, then it's just the anti-clockwise way. Okay? So we got two cases here to work on. Basically, just find the physical angle of one of them, and then you can just do plus or minus. Right? So basically, just find this angle using some geometry here. So yeah, I already did that. So let's draw this line, because remember circle theorem, that should be a right angle. The line drawn from the center to the tangent outside the circle like that is going to be perpendicular to that tangent. Okay, so we have a unit circle of 1 here. That is a right angle. Okay, and well, because this is -1 and this is 1, so this is length of 2. Aha. So this is a length of 2, right? So that means we have 1 and 2. This is, if this is theta, then this is the opposite and this is the hypotenuse. So sine theta equals opposite over hypotenuse. Yeah. That means theta should be pi over 6. Okay, just that physical size there of the angle. That means, do we get it already? Yeah. So theta is just plus minus pi over 6 basically. Yeah, because we need to get the tangent there. Just visualize that and you should be okay. Okay, part C. Hence determine the exact possible complex numbers Z. Okay. Wait, hang on. What is that? Given that Z also satisfy that. So it's asking the intersection, right? If I'm not mistaken. Yeah, it looks like that. Yeah, I think so. All right. So yeah. So I think it's asking for the intersection here because it satisfies both cases where it's 1 unit from the center of that circle and the argument from point -1, 0 is pi over 6, right? So we find that intersection and get the answer. Let's think about that, right? So, well, if we think about this in terms of Cartesian coordinates, right? Basically, we have a circular equation of x -1 squared plus y squared equals 1. Yeah, that's the circle equation of that thing. and we have this line right here. I mean, if we know this point, we know this point, right? Just work out the y coordinates. That is the opposite. So this point right here, what is it? It's the gradient. Well, you have to know that if this is a linear equation, right? The gradient of the linear equation would be the same as the tan theta, because tan theta would tell you rise over run. So tan theta here would be so tan of pi over 6, right? Tan of pi over 6 is just 1 over root 3. Yeah. So the linear equation would be 1 over root 3x. But what about the y-intercept? Well, we can just use this to just find c. Yeah. So that's plus c. So I plug in point minus 1, 0 in. So 0 here and minus 1 there. So this becomes minus 1 over root 3 plus c. So c is just 1 over root 3. Now we get the linear equation y equals 1 over root 3x plus 1 over root 3. Or, 1 over root 3x plus 1. Okay. Now what should we do? Well, so yeah, like this. Yeah, and then square this, equal 1. So just expand them all out maybe. X squared minus 2x plus 1, and this one is plus 1 over 3. X squared plus 2x plus 1 equals 1. I will multiply out by 3, so I get 3x squared minus 6x plus 3 plus x squared plus 2x plus 1 equals 3. Because the 3 would cancel the second brackets there. And then I would have 4x squared minus 4x plus 1, right? Yeah. Yeah, I guess using geometry might be a wiser way, but I didn't do that. I went for the algebra here. So this is 2x minus 1 squared equals 0. So x equals 1 over 2. It's a repeated root. Yeah, basically x equals a half there. So this is a half. Yeah, I could have used some geometry there, geometry trick there, and solve for that. But I went for this way, so I'm gonna go for this. Exact possible of the complex numbers. Okay, so if x equals a half, then y would be plus or minus, right? Because we have top and bottom part there. So if I plug a half in x minus 1 squared there, it would be minus 1 over 2 squared, which is 1 over 4. So y would be plus or minus square root 3 over 2. I mean, if you solve for this, like you move, you get 1 over 4 from here, so you minus 1 over 4, and you plus minus square root there to get y. Yeah, and that would be that. So that means the possible set complex number set here would be, the real part is just 1 over 2 plus or minus root 3 over 2i. Yeah, that would be the exact possible complex numbers, 2 of them. Okay. Yeah, that should be it. Number 6, prove by induction. Alrighty. Okay. Prove by induction for all positive integers n. So starting from n equals 1, yeah. So first step for n equals 1, we have summation from r equals 1 to 1 of r to the 3, yeah, equals 1 over 4 n to the 2, n plus 1 to the 2. Okay, so basically the left hand side is just 1 to the 3 because it's only one term, yeah, and the right hand side is just 1 over 4 times 4, which is 1. So true for n equals 1. Okay, so this is the first step. The second step is the inductive step. We need to assume that n equals k is true first. Assume true, the statement is true for n equals k. And then we're going to substitute k in there. Alright, so this will be sigma from r equals 1 to k of r cubed, right? Yeah. Well, this is basically, well, we need to prove left hand side equal right hand side, right? But if we assume that this is true, then we can write this already. It's not the proof step yet. This is just assumption, so we can use this. So that's going to be k squared, k plus 1 to the power of 2. Okay, and then we keep this result to be used later. So here for n equals k plus 1, now this is the inductive step now, is the k plus 1 step. So we have the left hand side from r equals 1 to k plus 1, yeah? And this would be r cubed as well, all right? Now, so this would be what? This would be r cubed, right? If we start from the first term. Now, I didn't influence from the, I didn't put the right hand side to the equation yet. I'm just going to consider the left hand side here separately for n equals k plus 1. Now you need to know that the summation on the left side is just from 1 to k plus 1. So it would basically be from, you know, you are substituting from 1 here, r being 1, and it's going to be cubed. And the next term will be 2 cubed, 3 cubed here. That's what it's saying. And then you're going to keep doing this until you get to k cubed plus k plus 1 cubed. I explicitly, intentionally put a k cubed here because before you get to k plus 1, you get to k first. So there's going to be a k cubed here first, and the next one is k plus 1 cubed. Okay, and this is it. This is the definition of this, yeah? Now, because we already know, don't we, that from 1, from the first to the k term is equal to that, yeah? So we can put that in, yeah? So we put brackets in here, and we know that all this is the summation from the first to the k term would be equal to that. So we will use that, right? Yeah? See that? And then we're going to do some algebra here to show that it simplifies to the right-hand side. So this is basically just proving from left-hand side to right-hand side. You can do the other way around, I guess, from right to left, but typically we should do left to right. It's safer, right? Okay, just the way I take it. So here you can factorize the k plus 1 squared out. So you get 1 over 4 k squared inside plus just k plus 1 in there. Yeah, because that's the only factor you take out. Now, wait, hang on. K cubed. Oh, no, that's right. Hang on. What went wrong here? It doesn't look like I should get that, should I? Yeah, I put this into this because that's the sum from the first to the kth term, and this is k plus 1 cubed. Okay. No. I should be proving that this is, okay. Sorry. I was mistaken. This will be equivalent to the n squared term. Now if I take 1 over 4 out of the second brackets, yeah, and k plus 1 squared here, I'm taking 1 over 4 out, yeah, so the inside the brackets I would have 4 k squared, right? Because if you multiply back, you should get 1 over 4. Wait, no. I should get just k squared, sorry. Because if I multiply 1 over 4 back, I get this. Just working backwards, and this should be then 4k, and this should be then 4, right? Basically. Yeah? So that means this will be 1 over 4 k plus 1, which is the n squared there. And this is what? K plus 1 and then plus 2. Basically, that's just k plus 2 squared. But I make it explicitly in this form because it's basically n. So when n equals k plus 1, this is the n and this is the n plus 1. Just according to that right-hand side form, right? Yeah? So this is true. True, right? This is true. So in the form, yeah, in the form 1 over 4 n squared, n plus 1 squared, like that. Therefore, also true for n equals k plus 1. Now the concluding step here, as it is true for n equals k plus 1 when true for n equals k. Therefore, yeah, since it is true for n equals 1, then true for all n being a positive integer. Yeah, that's it. Because that's the way you conclude the proof by induction here. Okay, and that's it for me. Next, question 7 seems like some calculus here probably. Yeah, solid revolution. Number 7, we have a balloon. Yeah, figure 1 shows a sketch of the balloon has height of 24 meters. Okay. Figure 2 shows a sketch of the curve C with the equation. Right. Okay. Equation this, yeah. This is a Cartesian equation where A is a constant. The balloon is modeled by rotating C, which is this curve, through 360 degrees about the y-axis. Well, okay. Given that one y-intercept of C is minus 12, right? So that should be 12, right? Because the height is 24 here. Yeah, makes sense. Show that A equals 144. A is 120. Okay, it's this one. Right. Okay, we got the. Okay, this is just to work on the equation first, part A. We know one intercept, y-intercept, so that means x equals 0. We put x equals 0 on the left side, we get 0, and then 12 plus y, which is minus 12, right? Squared. A minus 12 squared here. Just plug in the points basically. Yeah. Well, this will go to 0, right? So 0 equals, wait, hang on. That doesn't make sense. I get 0 there. Okay, hang on. Y-intercept is 0. X equals 0. Right. So that's trivial there. Right, yeah, okay. No, I should, Okay, I should use the fact that this is 12, right? I mean 24, so the other y-intercept is 12, 0, 12. Okay, so 0, 12 is on the curve here, because that's the height of 24, yeah? After you revolve the curve. So that means, I mean, it feels like this should be also 12, basically. Hang on. 12, yeah, I think it is. 12 and plus 12, yeah, I think it should be. Oh no, it's 1. Okay, hang on. I think, yeah, I know, right. Let me think about that a bit. So if we put 0 and 12 in, yeah, let's put 0 and 12 in. So put 0 and 12 in, we get this 12 plus 12 squared, and then A minus 12 squared. Yeah, all right, sorry. So this is 0 equals 1. Yeah, this will cancel the 0, so we ignore this part. We're going to have A minus 144. Yeah, A equals 144. All right. Yeah, almost flopped there. Okay, as required. Part B. Use algebraic integration to determine the volume of air needed to fill the balloon according to the model, giving answer to significant figures. So this is basically solid of revolution. Well, if you revolve about the x-axis, you would have this, right? But if you revolve around the y-axis, then you have the opposite, so it would be x squared dy. Okay, basically that. So you just integrate the thing. Now you already have the x squared to be this whole expression divided by 350. That's just the x squared. So I'm just going to delete that, yeah? Okay, so this is what? Pi over 350, because I divide across by 350 there, just to get the x squared part. And that would be just the right hand side there, which we know already a is 144 dy. Okay? And we should do the bounds, the limits from minus 12 to 12 here. Minus 12 to 12. That would be the limits of y, right? And we crack on this one, we should get the answer. All right, so 5 marks there. Okay, just some work. Now, how do we do this? Let's see. It feels like I can do, okay, if I can simplify this a little more, right? I'm not going to write the bounds yet. Well, here, right, this is 12 minus y and 12 plus y. Yeah, so one of them can merge into this, so I have even now 12 plus y cubed, just multiply by 12 minus y instead. Well, how that's going to help me? Well, if I do by parts, might make it easier. So I would do, I mean, I could go for this to be u and this is dv, yeah? So let's do by parts. So this is u, this is dv. Okay, so pi over 350 there. Then in big brackets, uv, so u is this, v is integrate of that, so I have 12 plus y to the power of 4 divided by 4. Just reverse power rule there, okay? And then minus, right, integral, yeah? Differentiate u, you get minus 1, so I'm just going to do plus here, yeah? And v again, which is 12 plus y to the power of 4 over 4 dy. Not done yet. Keep going with that. So this part is already fine, right? We just sub in the bounds and we should get the value there on this part. But this part we integrate, well, that's still reverse power rule again. So I get 12 plus y to the power of 5 divided by 5, multiply that with 4, I get 20 there. And that's it. We sub in minus 12 to 12 for that, all right? Yeah, so that should be it. How do we make the substitution a little easier? Is there a way there? Probably not, but if I look at each of the values here, the bounds, I mean, if you sub the upper limit, that will go to 0. This will not, right? So pi over 350, that would be 0 plus, so 12 plug in here, I get 24 over 20, 24 to the power of 5, yeah, minus the lower limits. If you sub 12 minus 12 in here, you get 0. Also here, you get 0. So that helps. That simplifies it. Okay, so we get pi over 350 times 24 to the 5 over 20. And let's use a calculator for that. I probably don't want to do mental math on that one. Pi times 24 to the power of 5, and then here 350 times 20. Okay, so 2 significant figures. That's huge. Height of 24, everything is in meters, right? Giving the answer into 2 significant figures. The volume. Okay, we should answer in cubic meters then. And that would be 3600. Yeah, if you round that to 2 sig figs, cubic meters. Yeah, all right, that would be my answer there. Part C. Modify the equation that to model a mathematically similar balloon with a height of 24. Okay, so this is a scale factor. Yeah, a scale factor, because the height is 1 dimension, so the scale factor is 26 over 24, because the previous height is 24, the new height is 26, so that is a factor there. Okay, you can simplify that, it's 13 over 12. Now, how does it change the volume? Okay, let me think about that. So the way it would change the volume would be if you only multiply this to this equation, you're only gonna multiply the volume by once. So you need to cube this thing, yeah, with a height of 26 meters. Yeah, so that would be 350 times x squared. I'll be back in a sec, yeah, something arriving. I'll be fine. Okay, sorry about that. Okay, yeah, because this is a scale factor, you need to cube this thing. All right, so you're gonna cube this thing. If you want to use the same limits, you're gonna cube this thing. Yeah, you're gonna have to cube this thing, and the volume will be changed accordingly. So it's still the same limit, right? Yeah. So that's just it. Okay, now do we need to simplify this? Well, probably not. It's just that, maybe. Well, okay, let's just get some idea there. That's a large number. 13 over 12 cubed. Yeah, I would probably go with that. Yeah. Wait, hang on. It doesn't feel right. If you, it's gonna stretch the y-axis by 13 over 12 times. So stretch the y-axis by 13 over 12 times while keeping the x-axis the same. Oh, but mathematically similar, so everything should be, yeah. I think this is it. I think this is fine. So let's check, let's do some sanity check here. If if we plug x equals 0 in, this whole thing would be 0, and the y coordinates would still be minus 12 to 12. So that doesn't give me 13. I should change it to 13 and 169 instead, maybe? Don't you think? That makes more sense, right? Yeah. But would the x be the same though? I mean, look, we could have something like this, at least on the right side. So 13 plus that, and that would be 13 squared. So that's 169 minus y squared. So that would make the y-intercept to be, yeah, that makes more sense. Hang on. Right. That's probably why. Because if I multiply both sides by that, yeah, it's gonna be this. This is basically from multiplying this by 13 over 12 cubed. So you're gonna have 2 of them in here and 1 of them here. Well, that's a bit weird, but yeah. I think I'm gonna go with that. But this probably will not be affected, so I'm gonna keep that as 12. And then I'm gonna have 113 over 12 here, and this will be this. Yeah. Okay. Yeah, that should be it, I think. That should be sound. All right. Part D. State one limitation of the model. Interesting. Okay, one limitation of the model. Well, what time do I have? Okay, 35, that's fine. One limitation of the model. Okay. Well, you see, there is a discrepancy here. I mean, if you actually revolve this shape, you're gonna have a shape like this, right? It's more like this. So this base part here isn't actually like the one you got from the model, because in the model here you don't have this horizontal part, right? That's one problem. Is there any other? Let me think about that. this model predicts what's x and y there? Right. Well, realistically speaking, I think this could be unrealistic if you talk about the actual balloon. It might not even be this shape. It might be even more spherical than this, right? State 1 limitation. Okay. I'm gonna go with the balloon might be more spherical. Okay, this is too elliptical somehow. It's not even elliptical, it's just some weird curve here. I don't know what that is. Some polynomial curve, right, on either side. This is a polynomial. So the actual balloon should be more spherical, right? I'm going to go with that. Although I'm going to also say that actually there is a discrepancy of the volume here because we didn't account for this. So this is actually larger because, you know what, I should go with that, right? Because if we consider this actual shape, it's just going to be this, right? So you see, this part here corresponds to this part here. And if you revolve, you're going to get just that. So you are missing a lot of volume there. If this is huge, right? So, okay, I think I would prefer that reasoning rather than this one. So there is a missing part of volume at the around the center, around the central, I would say central axis, yeah, of the balloon, right? So if we draw this, it is this very part here that we're missing. Yeah, that's the central axis of the balloon. We are missing it because if we have that shape, we integrate it to the other part, so it's just going to be this volume and this volume. So the center there is missing, right? Okay, that would be my answer. Next, number 8. Is that number 8? Yeah. The first n triangular number, that where n is a positive integer, use standard results of r squared and r summation, show that the sum of the first n triangular numbers is that, right? Okay, so r squared and r, right? So the sum of part A, the sum of r from 1 to n would be n over 2 n plus 1. We should know that. And the sum of r from 1 to n of r squared is, well, let's look at the formula sheet. Where's that? Hang on. Yep. Okay. So further math, page 9. That should be the formula. Where is it? Okay, here we go. Yeah, this one here. That looks almost like the thing we're proving there. Okay, so this is 1 over 6 n plus 1, 2 n plus 1. All right, so let's get back to the paper. Okay, now we are some of the first n triangular term numbers is that. So we are basically adding up this to this, right? Okay, so as you can see, this is how is it triangular? 2, 3, 4. Yeah. So the difference is 2, the difference is 3, the difference is 4. So the difference increases. This sounds like a quadratic formula here, quadratic sequence. Okay. So can I tweak that a little bit? No. It's a quadratic formula here, guys. Okay. Use the standard results to show that the sum of the first n term triangular numbers is that. Interesting. Okay, so let me do something. Yeah, I'm gonna mix between r squared and r. So if I have 1 plus 2 plus 3 plus 4 here to n, this is gonna be this guy, right? But then if I have 1 squared plus 2 squared plus 3 squared plus 4 squared plus blah 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 to n squared, it's gonna be this guy. Yeah. It appears like I probably should mix the two together somehow. So how about if I do n squared minus, this is 4. Okay, so how about n squared minus, yeah, the nth term would be n squared minus n minus 1. How about that? So if n equals 1, it would be 1 minus 1. Wait, no. Yeah, 1 here and minus, in brackets 1 minus 1, so that's 0. If n equals 2, so that would be 2 squared here, this guy, minus 1. We get 3, right? Yeah, we get 3. What about this? So this would be 3 squared, which is 9 minus 3 minus 1. So that would be, is it 6? No, it's not 6. 9 minus 3. 4 minus 2, 9 minus 3. 16 minus 4 is 12 and minus 2. Okay, hang on. This is 4. Hang on. So this is 12. Sorry, 2 squared minus 2 minus 1. This is 3 squared. I'm going to write the actual triangular numbers first. So 1, 3, 6, 10. Think about how we got that. Oh, hang on. Wait, the last one here. Okay, I forgot to consider the last term. We have 1 over 2n and n plus 1. What is that? If we simplify that, that's 1 over 2n squared plus n over 2. Does that work? Oh, that should, right? If we plug 1 in here, yeah, we get back to 1. If we plug 2 in here, that's going to be 2. That's going to be 1. Yeah, that works. Yeah. So basically, it's just this guy. Yeah, I forgot to just check that the nth term is that, right? So we're going to find the sum. Okay. So basically, the sum of this, yeah, all to that, will be equal to just the summation of what was that again? R squared over 2 plus R over 2, right? If you just expand that and put R instead of N, because wait, R over 2 here, sorry. Yeah, and then this R is gonna go from 1 to N. Yeah, that's it. So we just gonna simplify that. So we have 1 over 2 outside, and then this would be expanding the summation in from R1 to Rn of R squared plus summation from R1 to Rn of R. So it's just 1 over 2. The R squared formula would be 1 over 6 n plus 1, 2n plus 1, plus the formula for the R is n over 2, n plus 1, brackets. Okay, and we simplify that. So basically, yeah, we got to be clever here, so I'm not going to expand them, not yet maybe, but rather I would take maybe 1 over 6 out. How about that? I'm going to, well, yeah, I can take 1 over, hang on, n and n. Yeah, I can take n and n plus 1 out because they have a factor here. And see what I have left inside. So there's a 1 over 2 there already outside. So I have 1 over 6 still. This is 2n plus 1. Yeah, plus. Because that's all taken out, right? All left with is 1 over 2 there. Only the thing left in there. Yeah, so that's it. And we simplify the brackets. We would have n over 3 plus 1 over 6 plus 1 over 2, right? And that would be, so that would be 4 over 6 there on the last part, which is 2 over 3. So that would be 2 plus n plus 2 over 3. Yeah, that looks right. So we're going to have 1 over 6 there, 1 over 2 multiply 1 over 3, and then you have n plus, almost. Okay, and part B. Hence determine the value of n for which the sum of the first n triangular numbers is 22n. The sum of the first n triangular numbers is 22n. Alright, so okay, so this is the sum of the first n term. It's 22n, so I'm just going to do 22n like that, right? Equals that. Just equate them like that, yeah? Because the sum is 22n, right? Isn't that simple? Yeah, it should be that, right? And then we cancel the n. I mean, we don't want n 0 because that's 0 term, that's nothing. And then we solve this equation. So just move 6 to the other side. I get, multiply 6, I get 132 there. Equals, just multiply the quadratic there, n squared plus 3n plus 2. So this is instead n squared plus 3n minus 130 equals 0. Let's factorize that, can we not? Because we should be able to factorize. 130 is 10 and 13, right? So that's plus 13 and minus 10 because we need to get a positive middle term there. So n is just 10 while rejecting minus 13. So yeah, n is 10. That's it for this one. Next, number 9. We still have time. I mean, I took some time to just get the parcel there arriving at my house a while ago. So I lost some time there. Number 9, an engineer detects a source of water below the surface of the ground. The engineer models a situation relative to a fixed origin. In the model, the surface of the ground is a plane, okay, with that equation. All right. The source of water is at the point W with coordinates that. Where the units are meters, A, use the model to determine the shortest distance from W to the surface of the ground. So surface of the ground is a plane. We want to find the shortest distance between a point and a plane, right? Do we have a formula here? I don't remember. Hang on. Let me just get the formula just in case we have it. A point to a plane. Yeah, this seems like a perpendicular distance from point alpha, beta, gamma from a plane. Yeah, that's a plane, right? Yeah, it is a plane. Okay, so we're going to use this formula here, yeah? So the equation, I'm seeing the paper here, you don't, but alpha, beta, gamma is 6 minus 2 minus 4. And the plane, right? I'm just going to write the plane equation accordingly to the formula here. Yeah, that is 1x minus 2y plus 8z minus 1 equals 0. Okay, and then we are ready to plug that into the formula. So distance d is just modulus n1, which is 1, times alpha, which is the x coordinate, 6, plus n2 minus 2 times minus 2, plus n3, 8, times gamma minus 4, plus d, but d is minus 1, so we minus, divided by the Pythagoras of the, well, that would be the normal vector of the plane, yeah? Yeah, 1 squared plus 2 squared plus 8 squared there. Yeah, that's the normal vector there, is the 1, the 2, the 8 there. Okay, so that's the distance. We're just going to go back to the paper. All right, That would be the shortest distance. All right, so we just do that math. 6 plus 4 is 10. 10 minus 32 is minus 22, so that's 23 in the modulus there. Yeah? 6 plus 10, 6 plus 4 is 10. 10 minus 32 minus 20. Yeah, okay, I'm happy with that. Divided by the Pythagoras of that, so square root of 1 plus 4 is 5. 5 plus 64 is 69. So square root 69. That feels like I can use 3 to simplify that, can I not? 3 is 23. Yeah, that's exactly like, you know. Should I do that? Probably not. No need to. Yeah, I'm gonna leave it at that, yeah. The shortest distance. Okay, so we should get some significant, like some decimal answer here, just in case. Yeah, it's gonna be this, yeah. And then we just say, okay, 2.779. And this should be in meters, right? Yeah. Wait, 779? How is that? It should be 769. Yeah. Okay. All right. So B, by considering the model, comment on whether the answer to part A is reliable, giving the reason for your answer. Okay. Engineer detects a source of water below the surface of the ground. The engineer models the situation relative to fixed origin. Right. I'm just going to say that the ground might not be flat because the plane in the you know, the plane in linear algebra here is flat. A plane in math is flat, but the actual ground might not be. So the shortest distance might change, right? Because it may be shorter to some well rather than some peak, because if the ground is not flat, yeah. I'm just going to say the ground may not be flat entirely. That's it, maybe. Okay. To access the water, a hole is drilled in straight line from point P to the surface of the ground W. Point P, where's point P? It's just a new point, right? Given that the length of the hole needs to be as shortest as possible, determine the coordinates of P according to the model. Wait. The length of the hole needs to be as short as possible. Isn't that just the shortest length we found, right? Wait, hang on. But that's from the source. From point P. Point P is a new point, right? Yeah, just making sure. On the surface of the ground. From point P and from the surface of the ground. Given that the length of the hole needs to be as short as possible, determine coordinates of P. It's just, okay, this is the plane, and plane W, yeah? And the source of waters, this is point W. So basically, we are finding this point here, point P, where it's going to be perpendicular, yeah? Shortest distance. So how do we find that point? Determine the coordinates of point P. Okay, do we have a formula here? Let me just check. Okay, I'm looking at formula sheet, yeah. Plane through the point with position vector. So, okay, let's make that point A. The plane through A with normal vector and as Cartesian equation. Okay, yeah. I think we got one. We got this one here. This one right here. Maybe this one will be useful. So A is basically a point, and this is position vector of A, right? So it's just D equals minus position vector of P. I'm just going to do OP here, yeah. Yeah, OP, position vector, because we want to find the coordinates of P. So that's basically a position vector, dot product with the normal vector. And the normal vector of the plane we found earlier to be, yeah, is n1, n2, n3 here, the normal vector. Okay, so we got that already, which was 1 minus 2, 8, right? So that is just 1 minus 2, 8 here. Okay, that's the normal vector of the plane. And d here would be, the d on this side would be from the plane equation. It's just the minus 1 part again. So it's x minus 2y plus 8z minus 1. So d would be minus 1 here. Okay, that's the d. I'm going to cancel the minus there. So I have 1 equals. Well, basically you have a point where you do dot product, x, y, and z, like that. And then you should get 0 there. Okay, how do we do that? So it's just x, okay, 1 equals x minus 2y plus 8z. Oh, that's just the plane equation. Okay, I'm ghosted here. That doesn't help at all. I'm missing something, guys. I'm missing something. Yep, hang on. Oh, but if we find, okay, hang on. But vector PW here should be perpendicular to, and we already know the distance. Yeah, we already know the distance from the previous part. Hang on. Okay. Right. Let's assume that this is a normal vector in cap. Okay. Vector PW. We know position vector of W. All right, hang on. So should be 1. Okay, so I'm thinking because this must also be perpendicular to the plane, and normal vector is perpendicular anyway. So I'm gonna try something like PW dot N should be equal to, because they're parallel, so this should be a 1, right? Parallel cos theta 0. Yeah, wait, no, not 1. App PW, app N. Yeah, because this is basically that dot that. This is dot product equation, right? So just gonna write that again. So cos theta equals PW dot normal vector divided by modulus PW modulus N, dot product. And because theta is 0, because they're parallel, because both of them are perpendicular to the plane, so that goes to 1, right? That means absolute PW, we already know the distance between P and W is just, what was it again? Root 69 over 3. So I'm moving this to the other side now. And the distance of the normal vector, well, I mean the modulus of the normal vector is 1, 2, 8. So that's just 1 squared plus 2 squared plus 8 squared equals PW. P is just a point on the plane. A point on the plane. Point on the plane. How do we do a point on the plane? Should we make this a vector equation first? Of a vector, like, do we have a vector equation of a plane somewhere? Okay, this one got me. A vector, oh, we do, right? A plane through a point with position vector n parallel to B, and C has that equation. Parallel to B and C. I'm looking at the formula sheet basically. No. Am I missing something? Well, we know n here, it's 1 minus 2, 8, but this is x, y, and z. Dot product. Again, it's going to end up being the same thing, right? This is not helping. Probably not. All right. I'm gonna pass this one. Yeah. I'm still new to this thing. Yeah. Given that the actual length of the hole drilled is that, use the answer to part A to evaluate the model, giving the answer for your reason. The answer to part A, well, part A we have it, right? So part A was 2.769. Well, let's find the percentage difference. So 2.769 minus 2.52 divided by 2.769. Hang on, 2.769. So we find the percentage difference, yeah? And that is just 8.99%. Well, I would say that's quite far off. It should be within 1%. This is rather different to the actual, this in this case is the predicted value. It's rather different from the actual value, therefore not accurate, I would say. 8.99%. All right. Let's go back to the paper now. Question 10. I still have question 10, right? Oh no, 11 also. Oh, I'm doomed. Only got 7 minutes. Oh man. Okay. Oh, and it's still vector and plane. Determine the value of A. Okay, plane 1 equation that, plane 2 has equation that, where A is an integer. Given that plane 1 is perpendicular to plane 2, determine the value of A. Perpendicular, right? So their normal vector are also perpendicular. Okay, and normal vector. So normal vector plane 1 is just 1, 1, and minus 1. Normal vector of plane 2 is A, 3, and 5. They are perpendicular, so that means 1, 1, minus 1 dot A, 3, 5 should be 0. So A plus 3 minus 5 is 0, so A is 2. Okay, that's fine. B, the plane 3 has equation that, where B and C are integers. Given that 3 planes form a sheaf, what's that? If you don't mind, I'm just going to use a dictionary here to just translate that. Okay, a bundle. Okay, what is a pile? Right, a bunch, a stack. Like okay, it's like a prism, isn't it? Yeah, because the 2 planes are already perpendicular. So this one is going to be, okay, it's going to look something like this, right? Yeah, if we look from the side, it's going to be like that. Yeah, I'm assuming, maybe. Okay, I hope you understand, but yeah, so it's like forming like a prism there if you look from the side. But where A and B are integer, given that 3 planes, use algebra to determine B and C. Okay, so if we look, this is plane 1 from the side, this is plane 2, and maybe this is plane 3. Yeah, I'm assuming that this should be 45 degrees, because that's probably the only way it makes sense. So that means, how do we find that? Let me look at the formula sheet again. Okay, so okay, I don't think I can get this, and that's 6 marks. That's worrying. Okay, let's do number 11. Just gonna skip. Do number 11. I got 4 minutes. Let's see if I can make it. Okay, let's see. So roots here, okay, use algebra to determine the value of each of these roots. If x equals 2, and we have all that. So we know that similarly to quadratic roots, the sum of the roots will be equal to the minus b over a as well. Yeah, I'm just adding them up. And that is equal to minus b, wait, hang on, this is a cube. Yeah, it's still minus b over a, so 21 over 1 there. Okay? Okay, and then that's 3 alpha plus 9 beta equals 21. And the products, right? Alpha times alpha plus 3 beta times alpha plus 6 beta will be equal to, this will be negative, yeah, negative the last one over the first one. Okay? Yeah, because in quadratic it would have been the last one over the first one, but we put a minus sign here. Okay, so that's 91. Okay, so horrible. Okay, okay, I think I see something. This is simplified to alpha plus 3 beta equals 7. I'm just looking at the time basically. If we put that into this, we get 7 instead, right? That helps, no? Or I'm just going to go with, you know, alpha equals 7 minus 3 beta. That's horrible. 7 minus 3 beta. What do we want? Yeah. Okay, yeah, basically. 7 minus 3 beta. That might help. Alpha plus 6 beta equals 91. So we all get only beta now. So 7 minus 3 beta here. 7 in front from the second bracket. And this is, wait, hang on. I forgot to sub that. So that's 7 minus 3 beta, so plus 3 beta instead here equals 91. And 7 cut here, I get 1 and 3 here. So 49 minus 21, that's 49 minus 9b squared equals 13. So 9 beta squared equals 36, so b is plus or minus 2. If b is plus or minus 2, which one should we get? So alpha would be 7 minus 6 is 1, and that would be 13. So using algebra to determine the values of each of these roots. Is it 1? So I'm going to go with 2 and 1, yeah? Okay, 2 and 1. So beta 2, so that's 7. And then beta is 2, 12, 13. So that's it. Yeah, that would be my answer there. And I'm going to have to stop there because, yeah, my time is out, as you can see. All right, I'm going to mark the paper and go through the wrong ones if there are any, and the one that I didn't attempt as well. See you in a bit. Okay, guys, so I have marked the paper and I lost 13 marks. I mean, I'm not too proud of that because I didn't do 2 questions because I didn't know how to do it. And then there were some silly mistakes as well. We'll go through that. Yeah, the first one I got wrong. Yeah, everything is fine up until, yeah, the second one. Okay, so this one I misunderstood about this. Actually, the order of you know, getting the x-intercepts or the roots from z to 2z minus 1 is just to do plus 1 and divide by 2, right? So the roots, all the roots should be plus 1 and divide by 2. For example, if you do minus 5 here, so minus 5 plus 1 divided by 2, that would be minus 2. Would have been the correct answer there. And for the complex roots, if you do plus 1, so if you do plus 1 for the complex root, yeah, so it's going to be 8 plus or minus I over 2 plus 1, so that's plus 2 over 2. That would become 10 plus or minus I, yeah, over 2, and divide by 2, so you would get over 4 here. So that's actually 10 plus minus I divided by 4 instead. It was just like, so the idea is to make this a W maybe. So it's a transformed plane, complex plane, so it's a FW, yeah? And so the roots of W would be the roots that we got here, is the transformed root. But when we want to know what would be the z that gives the same root, so basically we are finding, so for the previous or the original z, that would give 0, right? Because these are the roots. So it was f of minus 5, f of, so one of the complex root would be 8 plus I over 4, no, over 2. And the other one is f8 minus I over 2. So we are finding the z value, yeah, that when you transform from each of the roots there, will also give you f0. So we are finding the z, so that we are finding all the values of z, so that when you do, so z equals something, so that when you do this, and then you get to that. So the first one, that's why we equate this to this, and then we solve. So the first one is 2z minus 1 equal minus 5. So that's why I get z equals minus 2. Because when you plug minus 2 in here, you get f of minus 5, and f of minus 5 gives you 0. Because these are all 0, right? They are all equal to 0. So basically, we are finding those new roots from the z here, that when it is inputted to this transformation, will give you minus 5, 8 plus I over 2, 8 minus I over 2. And those are minus 2 and these two complex roots. Yeah. So I lost minus 2 there. Okay. Not too proud. Didn't know that. Okay. And then this one. Yeah. I mean, I said to myself, right? I said in the video that, hang on. Let me just open the question here as well. I said in the video, right, that the determinant here is an absolute. So that means this one is plus or minus as well. Should have been plus and minus there as well. That means I should have also got the other two quadrants there when solving sine 2 theta equals 1 over 2. Right? So what are the other roots? Well, you would have also what? I'm just going to rub this off. And then you would have also 210, right? For the 2 theta first. So you would have 210 and then 330. And then if you add 360 from 210, you would get 570. And then 360 from 330, you get 690. Yeah? So those will also be available. Like, those will also work. If you divide those by 2, you get 4 more answers. Yeah. There are that many solutions to this one. Yeah. Because we know sine 2 theta is a half. But it's plus or minus as well. Yeah. Because the determinant can be plus or minus. And it will still convert the area to 1/2 times the original, right? So I'm saying that this could be plus or minus a half, because either case will work for converting the area to just 4.5, right? Okay, so I lost another one there. And then, yeah, I think the next one is this one, is the balloon here. So basically, yeah, this is wrong. It's just no 13 over 12 here and just put 13 in here. So basically, changing from all the 12 to 13. Now we're gonna work out why. Okay, so if you look at the shape again, let me just go to that question in here as well, just in case. It's actually quite simple, this method. So, but I didn't see it at the time. But it's just using transformation. Yeah, transformation is the key here. All right, but how do we do that? Yeah. So basically, I would make x the subject of the equation first for this one. Yeah. So it's going to be x equals square root of this whole thing. And a was 144, right? So it's going to be that divided by 350. Okay, so that's x. Now, function-wise, yeah, this is x as a function of y. Because don't forget, we have, it's like the sense of this curve is like we have a flip rather than y in terms of x. We have x in terms of y. All right, yeah. Now, if that is x as a function of y, right, to transform this function so that it stretches in all direction by a factor of 13 over 12, right? Because remember that was the factor there, because we want the height to be 26 rather than 24. So the scale factor was 13 over 12. Yeah. And in terms of transformation, we need to stretch along the x and along the y. So it's going to be 13 over 12 outside the function, as well as 12 over 13 inside the y here. Remember when we do something to inside the brackets, like the input, like the domain there, it's going to do the opposite. So if you multiply by 12 over 13, it's going to multiply by 13 over 12. If you multiply by 2 in here, you're going to have 1 over 2. And this will affect the y coordinates. So it's going to stretch the y coordinates by 13 over 2 over 12 times. It's going to stretch the x coordinate by 13 over 12 times. So we stretch both axes. Let's see what happens in terms of the expression here, because we get x as a function of y now. So if we have 13 over 12 f of 12 over 13y, that is going to be translated to, yeah, so basically just 13 over 12 outside the square root, yeah, and then in here will be the same. Now it's just basically substituting 12 over 13y into all the y's, right? So I mean, I'm going to substitute 12 over 13y here and then square that. So basically just substituting into this y, 12 over 13y, yeah? And the other one is also the same, but it's 12 over 13 overall squared first, and then close bracket like that. We simplify this, we should get the new expression, and that should be the way to go. Yeah. So if we can prove this, yeah, by checking, do a sanity check here. So if I substitute x equals 0, I should get y to be plus or minus 13, right? So the top bit here and the bottom bit here. And I mean, if we imagine, yeah, but the balloon will be stretched in both axes, it's going to look like this, yeah, roughly. And this will be minus 13. That will be 13. And this, yeah, if this is the x-intercept, let's say a, that's going to be 13 over 12a as well. We can check all those points. If they work, then this equation must work. Yeah. So let's do the y-intercept first. So that is x equals 0. So if I plug x equals 0, that is to put the left-hand side equals 0. That will cancel. The square root will be undone. Yeah. 350 will be undone. So I'm basically going to get this brackets equals 0 or this brackets equals 0. Well, because this brackets equals 0, well, yeah, we can do either one of them. So let's take the second one. This bracket equals 0, yeah. Would we get plus or minus 13? Well, let's see. So if I push that to the other side, I get this basically, right? If I square root on both sides, yeah, because I don't have much space here, I'm going to do this, square root on both sides. So this will be plus or minus 12. And as you can see, if you cancel 12 on both sides and you multiply by 13 on both sides, you get plus or minus 13 equals y. And that's the case. Yeah, so that's the case for the y. What about for the x? Yeah, for the x, so we substitute y equals 0. Yeah, that's the x-intercept there. We sub y equals 0, what happens? So x would be equal to 13 over 12 square root. Okay, y equals 0 here, so that goes away. We have 144 here because that's 12 squared. And then this one also goes away. We have also 144 there, yeah, over 350, right? Okay, so what is that? Well, we can use a calculator, right? Okay, so a calculator, 13 over 12 times square root of 144 squared. That would definitely be, you know, we already know that, I think. But then let's the calculator simplify that. So 78 root 14 all divided by 35. Okay. Now is this 13 over 12 times the previous one? Well, we haven't got the previous one, right? So the previous one, if we sub y equals 0 in here, what do we get? Okay, so square root, this is y equals 0, so that would be 144 as well. And that's also 144, right? The other part, that's 350. There you go. So you see, inside the brackets, inside the square root, it's the same thing. But this one is 13 over 12 of the previous one. The previous one is in the calculator. So that must be right, because it's 13 over 12, the previous one. I just proved it, so it works. Now the rest is just basically simplifying it, I think, right? Because we can't just write like this. I don't think so, because it's a modification of the original equation there. So we're gonna undo everything here and move it back to where they were. Yeah. So if we square on both sides, we're gonna get x squared. And imagine this will be 169 over 144. So that's going to be 144 here. Hang on. 144 here divided by 169 here. And this will be no square root, right? So the 350 will be moved back up here. Basically that. Yeah. And, you know, the two brackets here will just be 12 plus 12 over 13y squared, 144 minus 12 over 13y, and this one squared bracket. I mean, we could simplify it a little further because it doesn't look simple enough. So, you know, actually we could pull the 12 out here. So you see from this one, if I pull 12 out, I have two 12s because there are two brackets. So when I pull two 12s out, I get 144. Yeah. All right. And that would just be 1 plus y over 13 overall squared. Okay. Yeah. Well, if you simplify the, let me just delete this first. Okay. So if you simplify the other part, well, if we pull 144 out as well, right, that's going to be 1 minus y squared over 169, isn't it? Yeah. Okay. Well, seems like I can cancel at least one of the 144 there, this one and this one here. And if I multiply across by 169, right, what's going to happen? Yeah, I think if I multiply across by 169, I'm going to pair this to this bracket here. So I'm going to get, okay, you know what? Let me just, I'm just needing more space. I'm going to write down here if you don't mind. Yeah. Okay. So if I multiply 169 to the other side, I'm going to have the left-hand side to be 350 x squared equals, well, 169 multiply just this bracket because we need to choose. Well, this bracket, right? If you multiply by 169, it's like multiplying 13 two times because we have two brackets here. It's a square, yeah? It's a square here. So if you multiply 13 to each of the brackets, you get 13 plus y. And that's it. Already multiplied 169 there. You have 144 here. Yeah, so let me put 144 here. And this is 1 minus y squared over 169. Well, we could pull 169 out, right? We could pull 169 out, yeah. How about we pull 169 out? So it's going to be 144 over 169, 13 plus y squared, okay? And that would be 169 as well, yeah, because when you multiply 169 back in, it's going to be 1, and this one will just be y squared. There you go. So the a, which was 144, now becomes 169. The 12 here, becomes 13, and there is an extra factor here to make it work. So that's it. That's everything. It's not easy here, I would say. So this is the answer. Okay, that's the answer there. Just to make everything work here. Yeah. All right. But it's just 1 mark, so maybe you can skip this one. I would, maybe, if it's that bad. And yeah, this one you can answer basket volume here for part D, but I think the central volume of the balloon also works because it's miscounting. It doesn't account for the central part there. Or you could say the balloon might not be uniform, right? That's normally works there. Okay. And the next question I lost mark for because I didn't know how to do it actually. I mean, I tried something, but it didn't quite work, which is question 9, part C here. Well, let's look at the question again. Question 9, part C. Okay, question 9, part C, it's this guy, so that's the question there. And yeah, basically, I was almost there. I got the idea. So what should be right is to find, you see we have point W here, right, which is the source of water. We should find the vector equation of the line passing the W and the point P first. Okay? So let's find this vector equation. Of the line. Okay? Why do we do that? Because we can make this vector equation some variable and then put into the plane because the point P must be on the plane. So the point P is on this line and on the plane. Yeah? But we haven't got any idea about the line here yet. So how do we make vector equation of the line? Well, R equals A plus lambda B, right? And B is just a direction vector along the line. Now here's the key thing. Here's the critical point. The A is simple because it's just point W. We already know point W to be 6, minus 2, and minus 4. So that's just gonna maybe move it here. Oops. Yeah. So A is just 6, minus 2, and minus 4. Lambda is just some unknown to be found for each case. What about B? B is the direction vector. Well, what does the line look like it's doing? It's being parallel to the normal vector of the plane because don't forget, the water source to the P, the line joining these 2 points must be perpendicular because it's the shortest distance. That's the logic there. Because it's the shortest distance, they want P and W to be as close as possible. That means it must be perpendicular, this line. That must be the WP line here, must be parallel to the normal vector of the plane. Because the normal vector is also perpendicular to the plane. Alright? That means we can use the normal vector to be the vector B here, which is the vector, any vector that is along the line. Okay? So we're going to take vector B, the normal vector. So we got it from this thing here. So that's 1, minus 2, 8 there. Just the coefficients of x, y, and z respectively. And this is the vector equation of the line there. So it's just 6 plus lambda, minus 2 lambda, minus 4 plus 8 lambda there. And this vector equation works as something to tell you that if you want any point on the line, you can use this. That means point P with some known lambda will have this form for the coordinates. That means we can equate this to the plane equation because this must also be on the plane because P is on the ground. Yeah, so that's the next step. We're gonna put the coordinates x, y, and z there into the plane. Okay, so the x is 6 plus pi and so on. So the plane equation x is 6 plus pi already, and minus 2, y is minus 2 lambda, and plus 8, z is minus 4 plus 8 lambda equals 1. By solving this, we will be able to find lambda and hence find point P here. Okay, because we are asked to calculate the coordinates of P. So let me collect the term lambda here. So I have 1 lambda and 4 lambda there and 64. So lambda plus 4 lambda plus 64 lambda. And then the number term is 6 plus 4. Yeah. Right. And minus 32. minus 1 equals 0. So we have 69 lambda equals, on the left side. So this one is 10, this one is minus 33, so that's minus 23, right? Yeah. So we have 23 here. That means lambda would be 1 over 3. That's just divisible. Okay. Lambda equals 1 over 3. That means point P would be, or should I write OP first? Position vector of point P is just 6 plus 1 over 3 minus 2 times 1 over 3, and then minus 4 plus 8, 1 over 3. Well, we just simplify this set of coordinates. Let's just do, I can do 1 over 3 outside, right? And then if we add that, that would be 19, so 19 here. So minus 6 minus 2 would be minus 8 over 3, so this is minus 8. Minus 4 times 3 would be minus 12. Minus 12 plus 8 would be minus 4. That's it. So that's coordinates of P. Okay? So coordinates of P would be, let's move that. That's the position vector of P. So if we want coordinates of P, well, that's fine. It's just 19 over 3, minus 8 over 3, and minus 4 over 3. That would be the answer there. Okay? That's it for this one. Shouldn't be that hard if you know how to do it. Exactly. Okay, and this one is fine. Just comment on the reliability. Number 10 was a deal breaker for me because I had no idea what the sheaf was there. Okay. Number 10. So let's finish this number 10b thing, and then that's it, would be the whole thing. The thing was to have 3 planes making or forming a sheaf like that. It must be a linear combination. And by that I mean, so you must have like lambda and then plane equation 1 plus maybe mu plane equation 2. I write it just like pi. Maybe I should change that. Hang on. Lambda and then plane equation 1 plus mu plane equation 2 equals plane equation 3. Or, you can swap around, but that's the linear combination. Basically, this is something new, right? Or maybe not. Maybe you guys know it, but I didn't. Okay? And you need to plug in all the vector, the equation of the plane. So lambda, but you need to make one side equal 0. So for equation 1, right, it's going to be x plus y minus z minus 3, like that. For the second one, it's ax plus 3y plus 5z minus 4, like that. And then the other one is x plus by plus 13z minus c. And then we use component comparison to equate each of the components. So we simplify the x component and we equate to the other side, basically. And we do that for all other components. And then we should be able to solve a and b and c. All right, so let's just do them. So let's consider x first. We have lambda from the first one plus a mu from the second one equals the other side being 1. That's equation 1. We consider the y component, We have lambda from the first one as well. We have 3 mu from the second one. And then we have b for the right-hand side. Okay. For the z component, we have minus lambda, because you multiply this in, you get minus lambda, plus 5 mu for the second one, and then 13. That's the third equation, just for reference later. And then for the fourth one, the constant term, I'll just write c. So we have minus 3 lambda from the first one, minus 4 mu from the second one, and minus c from the right hand side. So basically it's just 4 equations and 3 unknowns. Solvable, right? Hey, hang on. Where's a, b, c, mu, lambda? Right. Okay, I hope we can solve this. Let me add a page first, yeah. Okay. Let's see. Okay, so if we add the second and the third, we're gonna have mu and b. Okay, maybe not. If we have the first and the third, we're gonna have mu and a. Interesting. How do we solve this one? Hang on. B and C. Yeah. Oh, we got A already. I forgot. A was 2. Yeah. Because look, it didn't make sense. We have 5 variables and 4 equations. That's not solvable. Now we have 4 unknowns, mu, lambda, b, and c. 4 equations, so solvable. That is to be called determinate. Yeah, determinate linear system. And yeah, so what should we do? So yeah, if we take the first and the third one, yeah, so let's do the first plus the third one, because I see that this can eliminate lambda. So on the left side we get 7 mu, yeah, just add them up, equals 14. So mu equals 2. Nice. If mu equals 2, then if we plug in the third one, right? Well, actually the first one. Well, I'll do the third one. I'm gonna get lambda equals 13 minus 10, and then minus, right? So that would be minus 3 in it. To 10, subtract, and then minus, yeah. Okay, so lambda is minus 3. And that would allow you to solve, well, let me check with the first equation, see if it works. Yep. So we can do the second equation to get b, yeah. So b equals lambda, which is minus 3, plus 3 mu, which is 2, so this is 3. And then for the fourth equation, we get c equals, well, if we minus the whole thing, if we simplify by minus 1, we're going to get 3 lambda, which is minus 3 plus, right, because I multiplied by minus 1, plus 4 mu, which is 2. So that would give me minus 9 plus 8, which is minus 1. And that's the answer there for those B and C values. That's it. Okay. Number 11, I cracked it actually with under 4 minutes. Yeah, I did it under 4 minutes. And that was it. So let's do a review here. I mean, this is the first AS core pure paper, further math core pure paper. So might not be able to compare from my experience that much, but I'm gonna compare it to the international syllabus then. I think the complex the complex number chapter here is okay. Just asking you to plot Argand diagram and do something. The transformation, however, could be tricky. If you take the observation that from point P to point Q, yeah, from point P to point Q, it's like switching the x and the y coordinates. I mean, regardless of the minus sign, you can maybe, get some feeling about maybe it's going to be a rotation, 90 degrees. And then you figure out the angle later, and then you figure out the origin later by just the way I did it. So I just worked out, okay, first I verified by asking whether this distance and this distance are equal, and they are. And then the angle, do they add up to 90? Yeah, and they did, so it works. Yeah, so that's the way to go there. Number 2, well, yeah, this is where I got wrong. The first one I got wrong. It's just the transformation here. So make sure you understand how I rationalize about, how you go from fz to z minus 1. When you already get some roots from the original fz function. Now, this one is quite different to what I see in the international syllabus. Yeah, it doesn't normally do this. So this is Yeah, this is tricky. This one, yeah, not that bad. You need to remember the inverse matrix of a 2 by 2. For the 3 by 3, it would be worse. It's going to be more tedious. Yeah, you will take some more time to do that. And yeah, this one is tricky because this one I forgot to do a plus and minus value here for number 4, right? Because you need to remember that when you do determinant can be plus or minus, but the area factor, we got to take that as a positive number. When you multiply to the previous area and get the new area, it's got to be changed to a positive number. That means the determinant could have been a plus 1/2 or minus 1/2. All right, so got to be careful there, and that's the key thing here. I think, yeah, the invariant thing, yeah, for B also important here. Yeah, you need to know that, right? Now for question 5, right, is a further Argand diagram here. Well, this one, yeah, you should know all the basic ones in terms of like the region you need to shade given a particular equation. So z minus something equals some number, modulus z minus something equals some number, that's a circle. Argument of something equals some angle, that's a half line. And then there's also modulus. So that's 2 other, right? So modulus z minus z1 equals modulus z minus z2. That's going to give you a bisector between z1 and z2. And that's about it for core pure 1, I think. Yeah. Okay. So make sure you know all those. And sometimes they mix the function together. Like sometimes they might do like, let's say they put this less than sign instead, and then and modulus z equals some k here. So that's going to be the intersected area. Let's do less than here inside a circle, and also less than some bisector line, right? You should see the example in the textbook. Yeah. Yeah, but then determine the possible here, the possible values. I think this one is fine. Yeah. Yeah. So this one is just basically finding the angle here and here of the tangent. Okay. This one is tricky, I think. This one. I mean, if you don't visualize that out, maybe you're gonna get lost then. And this one, basically, you need to know that what they mean is just to find the intersection between the circle and the tangents. So there are 2 points there. Okay. Yeah, this one I think is fine, proved by induction. So make sure you include all the steps, like the introductory step, the hypothesis step, like the n, assume n equals k, assume n equals k, and then the induction step, prove that is also true for n equals k plus 1, and the concluding step. So there are mainly 4 steps in any proof by induction question, right? It's going to get particularly tricky when you do it for divisibility proof. Yeah, I hope in the future I might be able to show you those if it appears in the paper, but yeah, look for those as well. Like make sure you can do those, you can nail those questions. But this is for just series. So there are series type, matrix types, and divisibility types in proof by induction that usually come out. Okay. Number 7, yeah, didn't get the scale factor part, but I hope I explained properly that. Everything else is fine. You need to know that if you flip the axis here, rather than doing integral pi integral y squared dx, we're doing pi integral x squared dy instead, right? And the bound should be from the lower y to the upper y. And if you do integration right, then you should get that. Now, if I didn't do by parts, I could have done, just expand them out. You can expand them out, polynomial, and then integrate each term. That might actually be easier than what I did here, I don't know, right? So if we can try that, so this is going to be 144 plus 24y plus y squared, and then just multiply this out with this guy. Yeah, might be. Ooh, maybe not, because hang on. Well, okay, maybe not, depends, because you're gonna have a lot of terms here to multiply out, right? You're gonna have like how many terms? Wait, this is y squared. You're gonna have 5 terms. Maybe not that bad, but the numbers are a little intriguing here, because you have 144 squared there. But I mean, I would write 144 squared. You don't need to write it out like that. And then, you know, expand all the terms. You should get 5 terms because this will be a quartic function. You integrate that, and then you should be home free. Okay, so this is up to you, right? Yeah, and I think I mentioned those. So the tricky bit, I think, is this guy, number part C here. Yeah, I didn't quite get that one. Number 8, almost didn't get the definition there that they have here in the first line. So basically, they already told you what to do with the n. That's the triangular sequence there. And basically, if you multiply that out, yeah, the key thing is to just multiply this out. So you got it to be this, and it's that. So that's the real critical point there, right? And then after that, once I know that, oh, it's actually r squared over 2 plus r over 2, then I can derive that correctly. Yeah. And then the second one, just equate to solve for n. That's right. Number 9. Yeah, number 9. The first part was fine. I needed to look at the formula sheet because I don't remember the formula here. The shortest distance between a plane and a point. Yeah. So that was fine. B, yeah, B. I mean, I couldn't quite crack that you would need to find the vector equation of the line first and then put it in the plane equation and just find the coordinate of C there. So that was a little kind of strange for me at first. And then D is just verifying. I mean, you could have said that is accurate within 10%. It's really up to how you say it. Yeah, this is just like practical. Alternative to practical if you guys do physics. Some of you should do physics here because this is further math. Maybe, I'm assuming maybe some of you do physics. Maybe most of you. So if you do physics, when you verify that it's accurate or not, you're going to have to refer to some number. So if this is where you say accurate, then you should refer to within 10% experimental accuracy. And this is also fine. I mean, I could have said reliable within 10%. But I said not accurate here because I think it's too far from 1%. I mean, mathematically, the accuracy, this is not physics, this is not science, so it should be smaller than 5%. And that's how I did that, and that was fine. Yeah, this one, no idea at all. But part A, it was just, yeah. So because the two planes are perpendicular, that means the normal vectors should also be perpendicular. That's why I dot product them and then got 0 there. So A was 2. And then this thing is a deal breaker here is forming a sheaf there. Yeah, it's just a linear combination. That is the key. So this line is the key when you have a sheaf thing here. And I think I explained it. So that was the hard part. And number 10. Yeah, number 10. Make sure you know the, just like the quadratic roots where the sum of roots is minus b over a and the product of roots is c over a. If you increase the order of polynomial, that also works, but it only works for the sum. So it's the minus b over a stays the same, but the c over a will alternate in sign. So for the second order, it's still c over a, but for the third order or the cubic function, it's minus c over a. For the fourth order, it's back to c over a, and so on. And this is not actually c over a, it's the last term over a. Yeah, it's only about the second term and the last term. So the second term divided by a would give you, minus second term divided by a would give you the sum of roots. And the last term, the coefficient of the last term divided by a, depending on the order there, plus or minus, would give you the product of the roots. All right, in this case, I got it. Yeah, that was just a little on the edge there, almost out of time there. But yeah, I nailed that one. And that was it, I think, the whole paper. It was hard for me because I didn't know how to do some questions. Basically, so I honestly have to admit that I have some knowledge gap there in those questions, but now I know, so not gonna happen again. So I hope if you have watched this far, so you find it useful, and please subscribe, and don't forget to see other videos in my channel. Just go check it out, and I'll see you in the next one. Bye.